Hey guys, welcome back. So today we're going to be talking about the composition of functions, how we're going to compose these functions, and their domain. So let's get started. Here we go. So a composite function is a function blank another function. So what we're going to be talking about is how we're going to be putting a function inside another function. So we're going to put here inside another function. So what compositions are, they're just functions inside of other functions. So when you see all these crazy functions, they're just a function that you've already seen with a little variation just put into another function. So the notation of this, and actually the way the book has it, and many professors go over it, it spells out fog. You see, it says F-O-G. But that's not very user friendly, and I don't feel like it's very easy to understand. See, the way I like to think about this is that we're going to speak of this as F parentheses G of X, which means that we're going to be inputting G into F. So with that being said, let's change the color here of the G of X to perhaps blue, and we're going to show how the G of X is going to be called what I like to say the input function. And we're going to refer to the f of x as the parent function. So we'll be going back to this notation where I'm like, hey guys, this is the input function, this is the parent function, let's play with it. Alright, so now let's jump right into an example where we apply this concept. So here we have f(g) of x, right, in example A. But, like I said, that's not a very friendly notation or easy to understand, so we're going to change that to f of g of x, right? So what we're doing here is, right, we're inputting g of x, which is the input function, into f of x. So the way to do this, to make sure we don't run into any trouble, is I like to write out the parent function, which in this case is f, right? So f of x here is the parent function. We're going to put p here for parent, and g of x here is the input function, I for input, right? We're going to leave the parent function with an open parentheses wherever it has an x. So let's write that in there. We're going to have f of x, right, written as square root of x minus 1. So we do have an x minus 1 there, but we're going to leave an open parentheses where an x is supposed to go. And now we're going to input g of x where that parenthesis is. We're replacing every x in f with g of x. There's only one x here, so just one x to replace. So what we're going to do is we're going to input g of x in there. So since g of x is x squared, that's exactly what we're going to input in there. We're going to input an x squared here. So now this is no longer just f of x. This is actually f of g of x. So we have composed f of g of x by inputting g of x into f. That's just what it means. So we're going to clean this up just a little bit. So what we're going to do is we're going to rewrite this all in one color, f of g of x, and we're just going to get rid of that parentheses in those two different colors. So we're going to have one big radical with x squared and minus 1. And we're done. That's all they're going to ask us, to input one function into another. So now let's try a different example where we're just going to do it backwards, and by backwards I mean we're going to have a different input function and a different parent function. So here we have g of f, right? So that means gof. So I actually don't like the notation at all either, so we're going to change this to g of f of x, which in this case is a role switch, and we're going to have g of x as our parent function and f of x as our input function. While before, in the previous example, in letter A, f was the parent function while g was the input function. So things here changes just a little bit, but you're going to see the procedure is exactly the same. We're going to write out the parent function, which is, let's go back to red, which is g of x with an open parentheses wherever it has an x, so g of x here, and we're going to write out the function, which is x squared. So just one big parentheses and a square, because there's supposed to be an x there, but we're going to leave a big open parentheses so we can input the function we're trying to find. So here we're going to input g, we're going to input f into g, right? So in this case, f is square root of x minus 1, so we're going to input that right in here. And now since we have input f into g, where this is no longer just g of x, this is g of f of x. And the reason why I make the colors match is because now we recognize that f of x is the x squared root of x minus 1. So we have inputted where there was an x before with f of x. So let's now do a little bit of cleaning up, which is always nice to do. One color, g of f of x is equal to, here we have square root of x minus 1 squared. So we know that the radical and the square are just going to cancel each other. So all we're left with is simply x minus 1. And we're done. That's all we had to do. Just input the f into the g, simplify it a little bit, and we're done. So now let's move on to example 2, where it's exactly the same thing we were doing before. We're just going to be doing two different functions. So here we have a little bit of a fraction, and might get a little trickier. So it's going to be exactly the same thing. The only difference is it just might be a little more tedious. But let's get started. So in letter A again, we're going to be doing fog, or f of g of x. So let's write that in there, f of g of x. So I'm going to try to go as neat as I can here because I'm a little cramped on space, but I'm going to do my best. So here we have f again with an open parentheses, f of x, right, with an open parentheses wherever it has an x. So f of x only has one x, right, which is right here, the x plus 2. So I'm going to have 1 over parentheses plus 2, right? So what I'm going to do now is I'm going to input I'm going to find my input function, right? Which in this case we said the input function is the one here inside of the parentheses. G of x is my input function, and I'm going to input it into the parent function, which is f. So my input function, g of x, is going to go right in that parentheses next to that plus 2, and I'm going to have x plus 1 over x. You guys see that? So I'm going to have x plus 1 over x plus 2. So technically, we have already composed the function. We have stuck g of x into f, which lets us to remind, we need to change this into f of g of x, right? But now, actually, the hardest part of this is not the composing of these functions, but it's a little tedious algebra we need to do to fully simplify our answer. So in this case, we're going to have to work with the denominator because the numerator is just a 1. The numerator is just going to stay the same throughout the problem, while the numerator is going to get a little work to make it look a little nicer. So let's get started on that. So here we have the denominator. The first thing I'm going to do, since I have to add two fractions, I'm going to have 2 over 1, right? So I'm looking for a common denominator between x and 1, the two denominators, right? So the denominator there is going to be x. So choosing x to be my common denominator, I'm actually gonna try to go as neat as I can. X is gonna be my denominator, correct? I'm gonna put a plus in between them, and we're just gonna leave the first fraction the same because nothing was multiplied to the denominator of the first fraction. It was just x, and now it's x. However, for the second one though, we had 1, and now it's become x. So we literally multiplied it by x, so we're going to multiply the top by x. So we get in total here, we get a 2x. And let's write that in red, In red. Right? So, we continue by leaving the top the same. We're going to start up here again. And we're going to just clean up the bottom by joining the two fractions with one denominator, which is just x. That was the whole point of the least common denominator. And now adding the tops. So in the top, we have an x and a 2x. So it's going to add up to 3x, right? And then, let's put that back into the red color to stay consistent. 3x. And then we just have here this lonely 1, which is going to be a lonely plus 1, right? So right here is probably going to be the toughest thing to do to simplify because you're like, okay, I'm kind of done. I combine the functions, but you're not. A lot of professors will take away points for this, and it just sucks because you have the right answer. They just want you to keep simplifying and just play with the algebra just a little more. So you should do that. So here now, what we're going to do is we're going to divide, or actually just put an over 1 on the top. So the top we have 1, we're just going to divide it by 1, just so we can think about that we have two fractions, right? So in essence, what we have here is going to be 1 over 1, right, divided by this bottom fraction, right, that we have here, divided by this bottom fraction. Let's put a bigger circle over it. But whenever you divide by a fraction, what you actually do is you multiply by the reciprocal. So we're going to multiply by the reciprocal, which is x over 3x plus 1, right? So now we're going to multiply just straight across 1 times x. So 1 times x, that gives us x, and then 1 times 3x plus 1 is going to be 3x plus 1. So we're done. All we had to do is just multiply straight across for our last step, and we have finally simplified our composition. Although we were done in the first step because we technically have composed the function, we weren't simplified, so they would take off a lot of points. Alright, so now let's do exactly the same thing, but backwards, switching the input and the parent function. So here, the difference from from part A to part B is that if you notice, since f is a parent function in part A, we only have 1x in part A. But in part B, since g of x, right, since g of x, we're going to write this again. Since now g of x is our parent function, g of x has 2 x's. So I guess it's going to be a little more difficult because we have 2 x's to input versus 1 in example A. So let's just do that. So once again, we start always by writing the parent function, which is g of x, and we're going to leave a nice parentheses wherever there's an x in the parent function. So that's on the top right there, x plus 1, and the bottom right there is just x by itself. So now we're going to input our function, which in this case is x plus 1 over x, and the bottom here is just x plus 1 over x. That's all we're going to do. And since we inputted our function already, there's no longer just g of x, it is g of f of x. Alright, so once again, we're done with the composition, but all we're going to do is simplify the function. So we're going to keep going down, we're out of space, go to the side. So let's do that. So now here we have the bottom looks simplified, but now the top has two things adding we need to take care of. So once again, we're going to start off by putting a 1 over here, and now we said the bottom is okay, so let's just write the bottom how it is, x plus 1 over x, but the top needs a little bit of fixing. So once again, we look for a common denominator in the top, which is going to be just between x and 1, it's just going to be x, right? So now we ask ourselves, sorry about that, it's going to be x for both of them. So now the first fraction, again, already had x, so it's going to stay as x plus 1. And the second fraction, it didn't have x, so we're going to multiply by x on the bottom, and we're going to multiply by x on the top. So this becomes x over x. Alright, so now once again, we just rewrite the fraction so we can keep simplifying. The bottom stays the same. And now the top, we're going to combine like terms on the top. So here we have an x and another x, so it's going to turn into 2x, and then we have this lonely 1 here, and that's just going to turn into plus 1. Alright, so now we're left with the same problem, that we have a fraction being divided by another fraction. So like what we said, when we have a fraction divided by another fraction, all we do is just rewrite the first fraction, or the top, the numerator. So 2x plus 1 over x times the reciprocal of x plus 1 over x. So it's going to be x over x plus 1. Alright, so now before we give a final answer, we can simplify something we see here, and we're going to be doing that by crossing out this x and this x. We're cross-reducing an x from the top to an x from the bottom, giving us our final answer to just be 2x plus 1 over x plus 1. And now we have successfully found g of f of x. Alright? So now, we're going to move on to not just composing functions, but finding the domain of these compositions. So, here we go. The domain of a composite function, f of g of x, as we like to look at it, is the union or the intersection of blank and blank. So first thing we got to discuss here is, are we going to look for unions or intersections? And between what? So the first thing we should look at is going to be intersections. So whenever we look for domains, we always care about the intersections of two different domains when we have two different functions. And I'll explain in a second. So the two functions that we're going to be looking at is the composite function, and the input function. So as I've been stressing, which one is the parent and which one is the input function, because when we find the domain, we need to find the intersection between those two domains. The answer that you get at the end, the composite function, and the input function that you have. So you need to look at those two domains. So we'll do an example real quick so you can see what I mean by that. So here we go. So first we need to compose f of g, right? So we start off with the parent function, f of x, equal to, there's just one x here, right? There's just 1 over x. It's going to be 1 over a blank. And now the input function is going to be, if you guys forgot here, we're going to turn this, right, into f of g of x, how we like it. So we're going to input, our input function is g of x. So we're going to input g of x into every x. So we're going to put an x plus 2 here. And now that we have composed the function, we change this to f of g of x. So we have now inputted g of x into f. Now, there is nothing to simplify here compared to our previous example. So we're done with the composition and its simplification. It's done. Now we need to find the domain. So like I said, we need to find first the domain of the composite. So when we look over here, right, we have 1 over x plus 2. This is going to be a rational function. And when we look at rational functions, all we care about, if we remember, is the denominator for domains. Correct? So we're going to look at this, and then we're just going to have the denominator not equal to 0. Because what happens if the denominator is equal to 0 in a rational function? We consider the whole fraction undefined. So we never want the denominator at the bottom to be equal to 0. So we solve for x, and we get x equal to negative 2. So that means that our composite function has a restriction that it cannot be negative 2. It can be any number, but not negative 2. Now let's see if our input, so this solves the domain of our composite. Now let's solve the domain of our input. Well, our input function is g of x. So our input, which is g of x, is equal to x plus 2. Now if you remember, polynomials, which is x plus 2 is a polynomial, they have no restrictions in their domain. So their domain has no restrictions. So it is all real numbers, or from negative infinity to infinity. So now we need to find, I don't like that line, sorry. And now we're going to find the domain of the composition. And what I mean by domain of the composition is the total domain, and by this I mean the intersection between this domain of the composite and the domain of the input function. So the way I like to do this, I'm actually going to remove myself from here. So so we give ourselves some space. So the way I like to do this is that I'm going to have a number line for the composite domain. I'm going to have a number line for the input domain. And it's going to be like our final domain. So what I mean is that I'm going to have 3 number lines, right? The first one is just going to focus on the domain of the composite. The second one is going to focus on the domain of the input, and then the final domain, which is the total domain of the whole composition, is going to be the intersection between the first 2 lines, between C and I. So I'm going to hide again, and the domain of the composite said that we couldn't have a -2. So I'm actually going to centralize. I'm going to centralize these lines by putting 0 in the middle of all of them, so we can have a little reference point there. So we can now have -2. So let's go to -2, and what it means is that we have a hole here at -2 because it cannot exist, but everywhere else you're okay. Everywhere else your function exists. Alright? Now we look at the input, and it has no restrictions, right? It's just from -infinity to infinity, so actually this thing has no restrictions. So now when we find the intersection, we need to combine these 2 number lines, and if we just squish these 2 lines together, we just kind of like put them right on top of each other. The only problem is that hole that we have at -2. Everywhere else they match. You see, if we look over here, for example, just random point, see, they match. They both exist there. They both exist here at 0. They both exist here. The only problem is right here at -2. So when we find the domain of the total function at -2, we're going to have a hole, but everywhere else it exists, right? So we're going to write this in interval notation or in set builder notation, whatever you like better. However, I do prefer interval notation, but I'm going to do both anyway. So interval notation of this domain is going to be all the way, we're going to be coming all the way from the leftmost point, right? So -infinity to -2, we're going to stop there. So -infinity to -2. We're going to put a union, so we connect it to the right side of this domain, which is from -2 to the right side of it, which is infinity. So from -2 to infinity. Then we have the interval notation, right? And now we have the set builder notation. It's going to be x exists everywhere except for -2. That parentheses looks a little ugly. I apologize, but there we go. So you have 2 ways to write this domain: an interval notation and in set builder notation. Alright, so now stick around for the practice sets, which we're going to be doing different type of composite functions, a little harder, and we're going to be seeing how how your professor can get creative with giving you some tough questions on composite functions, especially domain. If you're going to be looking out for domain questions for your test, most likely they will be coming out of the hardest compositions. They won't ask you a regular function, they'll ask you a really hard composition function, so you can actually think about the intersections of domains and other stuff that we just covered. Thank you. See you next time.